Today I want to give you another example of maximum likelihood estimation. Maximum likelihood estimation is outlined here, and we've gone over these steps. Okay, we're going to go over this example in which we're asked to find the maximum likelihood estimator for sigma, where the data comes from a normal distribution with known mean equal to 0 and unknown standard deviation sigma. So we're asked in our first step, well, our first step is to collect data, but that's done here. Okay, so first we have data. The second step is to form the likelihood function. So we're going to start there. But one thing that we're going to note is because our data comes from a normal distribution with unknown sigma, each of our observations, f of xi, has probability density function given by a normal distribution with mean equal to 0 and unknown standard deviation sigma. So this will be minus xi squared divided by 2 sigma squared. Okay, that is the density function for each of the normal distributions, and you just need to look up the density formula. So if we want to form the likelihood function, which is a function of the unknown parameter sigma, this will be f of x1 all the way through f of x sub n sigma. Now, if we write this out, the density functions will be multiplied n times because there are n observations. And we have n of these. Okay. Now, just doing some algebra, we're going to have 2 pi. Each of these is to the 1/2 power, negative 1/2, but there are n of them. So minus n over 2 times sigma to the minus n. Then in our exponents, the exponents add. So I'm going to have minus x1 squared minus x2 squared minus x sub n squared divided by 2 sigma squared. Okay. Now, in the example above, it says take the derivative, set it equal to 0, or take the log of the likelihood and set that equal to 0. So here, the log of the likelihood is going to be the log of all of this. And we can use the properties of exponents. Okay, now multiplications become additions. So this will be ln of 2 pi to the minus n over 2 plus ln of sigma. Now instead of putting that to the minus n, I'm going to bring that exponent out in front. That's one of the properties. Then I'll have plus the ln of e. But ln of e, those are inverses, so I'll have minus summation from I equals 1 to n of xi squared divided by 2 sigma squared. Now, what we have to do is take the derivative of this. So we're going to take the derivative with respect to sigma. Because I differentiate with respect to sigma, this first term does not involve sigma, it's 0. Now I have to differentiate ln of sigma. That will be 1 over sigma from calculus 2. This last term, remember the sigma's in the denominator, so that's really sigma to the minus 2. So this will be 2 times the summation from I equals 1 to n of xi squared divided by 2 times sigma cubed. The exponent comes down, that's the negative 2. The new exponent is negative 3. And I put it back in the denominator. Okay, so I set this equal to 0, and I try and solve for sigma. So multiply both sides by sigma cubed. And that will give us minus n times sigma squared. The denominator goes away, so I'll have plus summation from I equals 1 to n of xi squared equals to 0. Now all we have to do is solve for sigma. If we solve for sigma, we'll get sigma squared is equal to the summation from I equals 1 to n of xi squared over n. Now, if we want to just get sigma, I'll take the square root of all of this. We'll get summation from I equals 1 to n of xi squared divided by n. And what this says is take all of your observed values, square them, add them up, divide by n, then take the square root. That is the estimator for variance. And this is your maximum likelihood estimator.